Welcome to our CathCAD software training series of videos. This video will detail the concept of modeling multi-layered composite tubing using the CathCAD software. The agenda for today's training video consists of the following 4 items. First, we will provide a brief introduction to the CathCAD software. Second, we will provide some simple published multi-layered composite catheter designs. Third, we will provide an example of decomposing a braided composite tubing into layers. And finally, we will model a multi-layer design in the CathCAD software. CathCAD is the software solution that allows the user to analyze and predict the mechanical characteristics of microcatheters. The computational algorithms are based on the following models and/or data sources: mechanics of materials, composite laminate theory. Tube buckling or kink radius computations are based on the model developed by Brazier in 1927. Vendor material data sheets are used for loading material properties for standard materials used in medical catheter products. These data sheets typically provide the material properties at standard conditions. And the software computational engine is not based on empirical or tabulated measurement data. The CathCAD software adheres to or follows the ANSI SCTE 51-2007 standard. This standard states that a fully described braid layer consists of 3 parameters. The first parameter is the pick count, which is measured in picks per inch. Pick count refers indirectly to the density of the braiding pattern. A high pick count produces a denser pattern, while a lower pick count produces a braid pattern that is less dense and the surface area coverage is lower. We will be providing a separate training video on the various braid patterns provided by the Steger braiding machines and how to exactly model them in the CathCAD software. The CathCAD software provides a measurement of braid density by computing the surface area coverage. A value of 0 indicates that the surface area coverage is 0, which a value of 100 indicates that the surface area coverage is full. The first example is the subline microcatheter. It consists of 4 layers. The first layer is PTFE inner liner that provides smooth device tracking when advanced over guide wires. PTFE inner liners are typically on the order of 0.00075 to 0.0015 inches in thickness. The second and third layers are a dual stainless steel braid layers. The company did not specify the wire size of the braid. The matrix material, or the material that fills the braid layer, is the outer polymer outer jacket material, which is not specified. The fourth layer is the out polymer jacket material. In most cases, this material is a Pebax or nylon material, or may vary along the length of the microcatheter. The summary lists that the outermost layer is a hydrophilic coating material. This coating is typically so thin and does not impact the mechanical performance of the device, and so it is neglected when modeling the device in the CathCAD software. The next device that is evaluated is the March guiding catheter. Its design is very typical for a guide catheter. The first layer shown in the design is the PTFE inner liner. As in the previous example, the typical thickness is 0.0075 inches to 0.0015 inches. The second layer is a stainless steel braid layer. The braid matrix material, or the material that fills the braid layer, is the proprietary polymer blend material that is shown in the figure. The third or final layer is the material that sits on top of the braid layer, or layer 2. This layer is the proprietary polymer blend material, which is not specified. The design shows a soft tip in the design on the distal tip of the guide catheter. This soft tip is typically not modeled in the software, as it is usually very short in length. Based on the prior 2 commercial examples, we observed the general principles when decomposing a design into its individual layers. We now will provide the following example, where the design is decomposed into 4 layers. The first layer, or layer 1, is the inner layer, which is identified as a clear material. In many microcatheter designs, this layer is a PTFE layer. The second layer is a tie layer that sits between layer 1 and layer 3. It is shown as a blue material. Tie layers are used to bond 2 dissimilar materials together that would otherwise have poor adhesion to each other. If the tie layer thickness is thin as compared to the overall dimensions of the design, it may be ignored in the CathCAD software. Layer 3 is the braid layer. The braid layer matrix is the dark blue material that is sitting on top of the braid layer. Finally, the outside layer, or layer 4, is the dark blue material. How can the user decompose an existing design or a new design into layers in order to use the CathCAD software to model it? We provide two methods to solve this problem. First, the information may be provided directly on the engineering print for the design. If the design is made by a contract manufacturer, you may be able to contact them directly and obtain this information. Many contract manufacturers are licensed users of the CathCAD software, and they may have already executed your design and/or can provide you this information. The second and more probable path for decomposing the design into its individual layers is by directly and indirectly computing the layer dimensions by measurements and/or from the design. As an example, we provide the process for a 3-layer design. First, we will measure and/or obtain the inner diameter and outer diameter of the design. In our example, the first layer is a PTFE layer, so we will obtain its thickness from the engineering print and/or from the supplier of the material. The second layer is the braid layer. Its thickness is defined by the braid layer. If the braid wire material is round, the thickness of the braid layer is twice the braid wire diameter. If the braid wire material is of a flat wire nature, then the braid wire layer thickness is twice the braid wire thickness dimension. The CathCAD software automatically computes the braid layer thickness based on the dimensions of the braid wire selected for the design. Finally, the outer layer may be computed from the ID/OD and the layer thicknesses determined for layer 1 and layer 2 as shown. We have observed users of the CathCAD software make mistakes in entering the dimensions of the outer layer of the design, specifically if the outer layer is applied to the design using the lamination process, which is sometimes called the fuse down process. The user makes a mistake by entering the dimensions of the tube prior to the lamination process into the CathCAD software. This process results in a significant error as the resulting OD is incorrect. In order to prevent any modeling errors, the dimensions of the model design as entered into the CathCAD registered trademark software is that of the finished design after all manufacturing and process steps are completed. We will now execute the modeling of a 6 French guide catheter design into the CathCAD design. The number of layers is exactly 3 as shown. The inner diameter is 0.0630 inches. The outer diameter is 0.0745 inches. The two-wall thickness is 0.00575 inches. The first layer is a PTFE layer with a wall thickness of 0.001 inches. The second layer is a braid layer. The braid wire material is 0.0015 inches round. The braid wire thickness is thus 0.003 inches thick. The outer layer or third layer is computed from the wall thickness of the design by subtracting the layer 1 thickness and layer 2 thickness as 0.00175 inches. The design is entered into the CathCAD standard software as shown in the screenshot. The user will note that the tubing outside diameter is automatically computed. This value should be compared by the user to the expected design to make sure they are the same. If they are not the same, that means that the user has made an error entering the design into the software. The viewer should also note that the braid layer thickness is automatically computed by the software. The braid layer thickness does not have to be entered into the software. When the design is fully entered into the software, the user may select the Compute button and the CathCAD software will analyze the design in a few seconds. The screenshot shows the outputs after the user has selected the Compute button. A number of features or menu items show up after the software has analyzed a design. First, the pick count menu may be used to evaluate a range of pick counts for the design. This menu option allows the user to optimize and find the best pick count or braid density for the design. Second, the user may use the CathSolver function in order to optimize the design. CathSolver is a relatively new feature and its use and capabilities are detailed in a separate training video and/or training guide. Third, the user may select the Export to Microsoft Excel function. This menu exports the design directly to Microsoft Excel in a format that allows the user to easily compare designs. Finally, the user may select the Ovalization Summary. This function provides details of how the design will deform when it passes around a prescribed bend radius. The user is referred to a separate CathCAD training video where we fully discuss the CathCAD software's output parameters and what they mean. This completes the CathCAD training video. For more information, please visit our website at www.cathcad.com.